Good. Okay, so I said we'd spend the first part of this meeting discussing what we voted on to do next after we finish lesson 12. And it looks like, let me quickly look, I think that the FastAI natural language class came out the winner. Let me just make sure of that. Let's see, the voting. Let's see. Yeah, it looks like what I see is the final votes are natural language. The FastAI natural language class got 12 votes. The next one was Kaggle projects got 9 votes. FastAI version 2 library, studying that, got 8 votes. 3, 4. MLcourse.ai got 1 vote, and FastAI course number 1 got 4 votes. And those are all things that I would like to do, but it looks like what was voted on was that we would do the FastAI NLP class. So any thoughts on that or reactions to that?
I don't know. This is just my personal taste. I'm not that much into NLP, but I mean, I'm a democratic guy, so the majority has voted, I guess.
Yeah. So, but like I said before, there's since we had 12 votes for number 1 and 9 votes for Kaggle competitions, and there were 8 votes for the FastAI version 2. So I think that we could, like, if anyone wants to start either or both of those activities, we could go forward with in parallel with all with 1 or 2 or 3 activities.
Yeah, I think that's a good idea.
So I'll just leave that up to everyone. If anybody wants to lead either the Kaggle competition activity or the FastAI version 2 library walkthrough part, then they can do that, and you can set that up on the FastAI DL, on the Slack channel that we're working on. So I'll just leave that for future discussion on that Slack channel. Okay. Okay, so I guess I set aside more time than we needed to discuss that. I guess we can. Is there any more discussion on that topic? Okay. Okay, then let's start discussing again, reviewing through these or passing through these 3 notebooks again. Quickly, I mean, I want to pass through I want to spend some time on each one, so let's see how far we get. So I'll start to share, and there's this one. Share, but I want to, oops. Okay, so I should be sharing the mix-up label smoothing notebook. Can everybody see that one?
Yes, I can see it.
Okay, great. So we talked about mix-up last time, and I think we spent enough time just introducing what it is. It's basically just expanding your training data by adding linear combinations of the training images. So, but I thought I'd go through just a bit of a because I cleaned up this notebook a little bit, and I thought we'd go through a little bit of it, so that anything that you didn't get last time, maybe you pick up this time. So the first thing after we introduce mix-up, then we are going to do we're going to do label smoothing. And so, or actually no, the beta distribution is being used for mix-up, so that's fine. So the beta distribution is used to generate the probabilities that, or the weights for each of the two images that we're mixing up. And there's a bit of interesting theory that goes behind this. So the first thing we do is we introduce this gamma function, which is just a generalization of the factorial function to all the real numbers. We talked about this a little bit last time. Everybody knows what 1 factorial, 2 factorial, and 3 factorial are, but what about 3.2 factorial? So the gamma function is a generalization of the factorial function to the real numbers, and that's plotted here. It's just the idea is that the gamma function is available in PyTorch. So actually, it's the log gamma function. So they create a gamma function just by exponentiating the log gamma function. So that's fine. And then this shows how the gamma function works. That it fills in the in between the integers. It fills in the factorial function. The next thing is that we introduce is this beta function, which has this complicated looking mathematical form. But the main thing to notice about the beta function is it's basically a U-shaped function. It's a probability distribution. And remember that all probability distributions have to integrate to 1. So the point has to be somewhere on the continuum from 0 to 1. And the only thing you need to know about this is that, okay, the beta function has 2 parameters, alpha and beta, but the way we're going to implement it here is we're going to make both of those parameters the same. And so alpha is chosen, and then beta is fixed to be the same as alpha. And when you do that, that's when you get this U-shaped version of the gamma function. Because the gamma function is actually a very versatile function, and it has many possible shapes. And what we're doing by setting the 2 parameters equal, we're getting these U-shaped functions. And why do we want a U-shaped function? Because we want to choose our probabilities so that they're near 1, that they're not too far away from 1. And so, if the probability of one of the 2 images, of mixing up these 2 images, the probability of one of them, we want it to be close to 1, and the other one, we want to be close to 0. So that's nicely satisfied by this gamma function, because we can choose the first one is, either you choose something that's near 1, and then you can subtract it from 1 to get something that's near 0, right? If you have a high probability like 0.9, then 1 minus 0.9 is 0.1, so that's a low probability. Or if you happen to choose a low probability of, let's say, 0.1, then subtracting it from 1 gives you the high probability. So the gamma function the beta function is ideal to choose the mix-up probability. And this is just showing what happens with different alpha parameters. You can get a softer and softer U-shape. That means that some of the probability, with the very hard U-shape here, most of the probability is very close to 0 and 1. But as alpha decreases, you get less of the probability concentrated near the 0 and 1, and some of it concentrated nearer to the middle, you see. So that's all this parameter does for you. And so what they do is, I think they choose 0.4 for their experiments going forward. All right. Just wanted to show something about label smoothing. I rewrote this section on label smoothing because there was some confusion about how they talked about it, and how they actually implemented it. So I cleared that up. It looks like there's 2 possible ways to implement the label smoothing. One is described in section 7 of the Inception paper, and the other one, that's what I call method number 2. And method number 1 is talked about in section 5.2 in the Bag of Tricks paper. And they're very subtly different. But let's just talk about that for a moment here. the first one is so the whole idea of label smoothing is to add some noise to the training labels, but not too much noise to get it all confused. You want to just add a little bit of noise to the training labels. And why is that good? It's basically because it's a regularization. Whenever you add noise to your either your training images or your training labels, it gives you some regularization. And what that means is it doesn't tie the model, the fitting down to the data so much, because it's not even getting it's not getting the data, it's getting a noisy version of the data. So that makes it less likely that it's just going to overfit to the way the data is, to the way the data looks. Does that make sense? So we're kind of messing up the data a little bit, so that it won't learn the data, and therefore it won't overfit so much. So that's why label smoothing is called a regularization technique.
Joseph, a question
yes.
back on the even before label smoothing on just the mix-up part. Is it clear to anyone else as to why he says that the one-hot encoding, we go to some trouble in PyTorch to not do it, and therefore introduce label smoothing? And the reason I ask is, if you read the mix-up paper, it actually says that the label smoothing version underperforms the one-hot version. So usually Jeremy is like after every inch of performance. In this case, he's backing off from it, which I find surprising. And the second part, there was just a paper published or a reference to it, which says that transfer learning is actually worse with models that are trained with label smoothing compared to non-label smoothing, which is something, again, given that he uses transfer learning so much, I would think he would want that extra ounce of performance by using one-hot labels. There are other reasons. I mean, generalization is a big reason why label smoothing helps, and that I understand. But I was just curious whether somebody else has a comment on, anyone has a comment on why one-hot encoding, he comments, is avoided so much in PyTorch.
That's a good question. I didn't pick up those subtleties. So just to review, you say that that in the original mix-up paper, it says that one-hot encoding does better than label.
Yeah, in the various combinations, they show that the original, and even he has it here, that what the original paper says in the 4 bullets in the notebook, he says that one-hot encoding is what it suggests. But if you, but then he goes on to implement label smoothing, which I understand, just below that, just below where.
Sorry. Okay, so just below.
There, right there, 4, bullet point 4, just above the note on gamma function. There, use one-hot encoded targets.
Oh, I see. One-hot.
Okay, but that's, now they also show with label smoothing and refer to the same CZD paper, but it's kind of interesting that their performance with one-hot encoded is better. And then there's a more recent paper, I'll post it later on the Slack, which tries to explain what label smoothing does. And essentially, by the way, that paper seems to suggest what label smoothing does is it links the error of the non-correct classes to the correct class and bounds it with a constant, with the result that the correct class is not allowed to go all the way high, as high as it would wish to go otherwise. And that helps regularize or generalize the results in other applications, meaning in, when it's used with other images, for example. So if you can.
Yeah. So I'm a little confused about what you mean by what he means by use one-hot encoded targets. Does that mean just not use label smoothing?
Yes, because
so you just use the target as either a definite label or not.
Yes. So, or use the majority image as the image to be recognized.
The majority image.
Meaning, if you use
the one with the highest mix-up.
Exactly.
Coefficient.
Yes, that's what the paper says.
I see.
from my understanding of what Jeremy said when he said you mix up like say 0.7 of tench and 0.3 of the gas pump, you basically replace one hot encoding with like a 0.7 where the tench is and then a 0.3 where the gas pump is, but you keep everything else as 0. So I don't know if that is what the one hot encoding, because implementing that in PyTorch is not possible because I think PyTorch pushes for literally having one in the place of instead of 0.7, so you can't have floats over there. So yeah, I think there are a lot of different things and interpretations, like what Joseph was asking, like what exactly does this one hot mean? Does it mean put a 1 in the place of where the tench is 70%, or does it mean put 0.7 and 0.3? So yeah, that's what kind of I understood from that conversation.
Yeah, when I was going through the code for Mixup, I kept thinking, okay, he mixes up the images, he mixes up the training data, but he doesn't mix up the labels. There's nowhere where he actually mixes up the labels and calculates, 0.3 of the tench label and and 0.4 of the other, 0.7 of the other label. What he does do, where I think it works, is it mixes up the loss functions.
Right,
So,
exactly.
So yeah, so you calculate the loss function for one image, and then you multiply it by 0.7, and then you calculate the loss function for the other image, and then you multiply that by 0.3, and then you add them together. So I think
which in effect should be the same thing.
Yeah, because that's all you're using. The loss function is just it's the same as one hot encoding, right? It's the same as setting the image to be one thing and then calculating the loss function, and then setting the image to be the other thing and then calculating the loss function, and then mixing them together with the two rates, right? So
yes.
that's how I understood mix-up, but maybe mix-up with one hot encoding means don't do that. Calculate the loss function based only on the most probable image. Is that seems to be the understanding that I think it was
Isn't there a point where in the lecture Jeremy mentions that you don't want your model to be predicting something as 1, but you just want it to be like 90% confident?
That's the label smoothing. That's the label smoothing part, right?
Oh, okay.
Yeah. So so let's leave it at there for now, but that's a really good point that Srinivas raised, and I haven't read carefully the mix-up paper, so maybe I should do that to understand what they mean by one hot encoding. And Srinivas's point is taken, because Jeremy's always going for every last drop of speed, and then all of it. So why would he develop this if it not only every drop of speed, but every drop of accuracy? So why would he develop this if it's not accurate, if it's shown to be less accurate than doing things with another method like one hot encoding? So I don't understand right now what the comparison is, between mix-up and one hot encoding. So maybe I have to read more about that. But anyway, let's go back to this label smoothing to try to understand what it is. So this is where Jeremy is saying you want to make the model less certain of its decision. And the way you do that is you, instead of assuming that, that an image is just one thing, that the label is just one thing, you say, well, the label is either correct with very high probability or incorrect with a very low probability, and you form a mixture distribution. So, and the mixture distribution is epsilon is set to be 0.9, 0.1, some small number. So 1 minus epsilon is a large number, and so with 90% probability, then the loss function, you calculate the loss function assuming that the label is the correct label. So, if you were doing this without label smoothing, this would be 1, and then the next term wouldn't be there. There was epsilon would be 0, and that would eliminate the second term. But with epsilon to be 0.1, then you're saying, okay, there's mostly the correct label, but there's a small amount of incorrect label. That is, the label is any one of the incorrect classes with equal probability. So that's why I divide by k minus 1, because there are k minus 1 incorrect classes, where k is the number of classes. I think I said somewhere. I should have said, yeah, k is the number of classes, and I is the correct class. So and then L, this script L is the standard, is the cross entropy loss, and it's just minus log probability. Remember that. Okay, so mix-up is basically, label smoothing is basically forming a mixture distribution of the correct label and the incorrect label, but with the correct label has a high probability or a high weight, and the incorrect label has a low weight. Does that make sense? Okay, I'll let that percolate for a while. Speak up if you have any questions. Then the second method is slightly different. Instead of forming a mixture distribution with 90% of the correct class and 10% of the incorrect class, you say, well, it's 90% we know the label and 10% we don't know anything about the label. And if you don't know anything about the label, you would tend to set the probability of each label the same, right? You just basically say, well, there's k labels, so let's just say we don't know anything about it. That means the probability is to be any label is 1 over k. So it's really very similar to this one. And in fact, I implemented them both and ran 10 runs of each one and found that they're essentially identical. I didn't show that here, but the methods give the identical results. So it doesn't matter which one you like, pick one and go with it. It turns out that method 2 is the one they implemented below. And because you have to spend, it's a little bit easier to implement method 2, which is what they did. So that's fine, because I checked that both methods are the same. Any questions about them or comments?
Yeah, this is where there's a paper, as I said, I'll post, which seems to say when is label smoothing helpful and tries to kind of explain the math. I don't still get all of the math, but it seems to say that it basically ties the difference between the correct label and the incorrect label to be a constant. Therefore, the correct label is not allowed to be as high as it would otherwise be. And that in turn helps the generalization because it kind of fixes a constant between the value of the incorrect labels and the correct labels. It ties them together to be a constant. And that's kind of what is helping the generalization.
Again, I think I saw something about that in the original Inception paper. That's where I didn't read that paper. I just read section 7 where they discussed mix-up. And in that paper, he talked something about that too, that it's not, it doesn't let the correct label always dominate or something. And he also discusses, it's interesting, he makes a general statement of how you can implement label smoothing. And in that, he doesn't use a uniform distribution for the other labels. He said you can use any distribution you want for the other labels. It doesn't matter. Just something that's wrong, something that's not the correct label. But,
yeah, the other intuition that I found kind of very helpful is, they talk about, Jeremy also says this, that you reduce the confidence of the prediction of the correct label. And, for those of on the call who are kind of following along on the NLP class as well, where because of label smoothing, he says that the model is better calibrated. That is, its confidence in its prediction is better matches its actual accuracy of prediction. And where that matters even more is in NLP, you do a thing called beam search, which is you kind of search for the right set of values after you've done the prediction. And in that case, having a better confidence in your accuracy actually helps the overall result. So that's another way in which this label smoothing seems to help in NLP as well as in image recognition.
Oh, okay, that's a good insight. I don't know NLP. I don't know. You know, I'll find out about this when I learn more about NLP. But that's a good thing to remember. So you're saying that label smoothing helps you in NLP when you're doing beam search.
Yes, and that's because label smoothing helps calibrate the model better, which means that its prediction of accuracy is closer to its confidence in its predictions.
I see. So I see. Well, that's a good insight. Yeah, it definitely makes the model less confident in its predictions because it doesn't always let the model predict the correct class. It forces the model to sometimes predict, or it forces the model to sometimes predict the incorrect class with a small probability. So yeah, that's how it makes the model less confident in its prediction. I think that's what that does. All right. So the next thing I did was I just you know, I ran the, you know, he has training for one epoch for with label smoothing and without, but there's a lot of noise. So there's a lot of noise in the accuracy that you get from a single run. So I did this. I took an average of 10 runs with label smoothing. You know, of course, using the mix-up, and then but with label smoothing 10 runs, and then without label smoothing 10 runs. And I got these two results. I summarized them below. So I calculated the mean and standard deviation of the results. And you know, this is without label smoothing. I get this result, you know, 0.26 with a standard deviation of 0.08. And with label smoothing after 10 runs, I get 0.30 with a standard deviation of 0.05. So this is the summarizing the result. This is what I just showed you. But now, because we're doing 10 runs, we get to the standard deviation in the data, in the mean, you get to divide by square root of 10. That is, when you're trying to estimate what the mean accuracy should be, you get to divide by square root of 10. So the actual sigma, the actual standard deviation in the estimate of the mean is 0.03. And in the first, that is without label smoothing, and 0.02 with label smoothing. So now we can present the results this way. The mean, the determination of the mean accuracy is 0.26 plus or minus 0.03 without label smoothing, 0.31 plus or minus 0.02 with label smoothing, where these are the standard deviation and the means. And you can see that these results are separated by about 2 standard deviations. And so that tells you that you're confident that they're really different, you know, even when you consider the uncertainty. So they don't, their uncertainties don't overlap. And therefore, we would conclude that label smoothing does significantly improve accuracy. So that's the last thing I did here in this notebook. Any question about that?
Joseph, is this notebook available somewhere? It'd be interesting to have a look through some of the stuff you've done.
Yeah, this is on the GitHub repo, and its name is mix-up label smoothing _ JCat. Whenever I annotate a notebook, I always put _ JCat. I should have chosen some other word, some other suffix, but this is my version of the notebook, and the original version is just 10B mix-up label smoothing. So if you look in the Git repo, and I think I have a link to that in, I think I might have posted that on the forum. And I also posted a link to it on the Slack group too. So yeah, you can see my notebook if you go there. Is that okay then?
That's great, thank you.
Okay. So now I should go to the next notebook. Somehow I boxed myself in here. There we go. We'll go to the mixed precision. notebook. So here, there's a lot to understand. I did not go through the code in detail because I went through it. I started going through it, and then I realized this is going to take me a long time to go through this implementation. And so I think that the most important thing is to understand what the process is. What is he implementing here? So this is the diagram that he gives. Can everybody see that? The mixed precision training diagram?
Yes, I can see it.
Great, that means it's being displayed. Okay, so it's funny, after he shows this and talks about it, then he says something about how very easy it is to implement. And I did not find it easy to follow how he implemented it all. But where does he say that? It just
I got mixed up with where it was 32 versus where it was 16.
Yeah, so I think that let's discuss that part. I think if we can understand this diagram, if we come out of this discussion with an understanding of the diagram, that would be good. Here it is. Here he says, implementing all of this in the new callback system is surprisingly easy. So, what's surprisingly easy for Jeremy is not surprisingly easy for me, because I found plowing through all this stuff was really heavy duty stuff. And I got through part of it, and I just decided, no, I'm not going to go through this whole thing. So anyway, he ends up by forming a callback. He ends up by building a callback to do this mixed precision. And then, you can run with it. I wanted to run 10 to see if mixed precision was any better. And I found out that training with mixed precision, first of all, I found out that it's no faster than training without mixed precision. So I thought that mixed precision is supposed to gain you a speed advantage, and at least on my computer, it doesn't. It's 43 seconds for each epoch, and without somewhere back here we did it without. Anyway, I've seen the training without the mixed precision, and that's in the previous notebook. And it's also about 43 seconds, 44 seconds per epoch. So I'm trying to understand why it's not faster on my computer. And I think it's because I'm in Windows 10 and maybe it doesn't make full use of the GPU. Maybe that's the problem. But at least it works. Then I was running let's see, what am I doing here? Oh, okay. This first one is training without mixed precision. Sorry. And there it is, 43 seconds. I did a run of 10. Then I tried to do another run with mixed precision, and I ran out of memory. But I did see at least that with mixed precision, it's no faster. But the reason why I ran out of memory is because I was simultaneously working on another notebook, and I didn't have time to rerun this again. But it's not because there's anything wrong with the code. It's just because I was working on another notebook in another window, and I was using up memory in that one. So I got this CUDA out of memory. And I don't know, the best way to do this I find is just to back out and start again, just to close down the notebook and start again. I don't know if anybody else has any better ideas about what you do when you reach this out of memory error. Okay, no comments there. Okay, I'm going to go back to that diagram, but first I want to talk about this dynamic loss scaling that he does. So there's one part of this, we'll talk about it later when we discuss this whole diagram up at the top. Sorry if I'm making you dizzy here. Where you multiply the loss by some large number, and he uses 512 or something for that number. And the reason why you do that is because the loss can get very small, and also the gradients will be very small. And the reason for multiplying the loss function by some constant is so that the gradients will be artificially made larger. Because when you multiply a number by, if you multiply a function by 2, then all the derivatives get multiplied by 2, right? Because say if you have x squared and the derivative is 2x, if you differentiate 2x squared, the derivative is going to be 4x. So scaling the loss function is the same as scaling the gradients. And I think that's the reason why he does it. He wants the gradients to be larger so that they don't underflow. Okay, but let's leave that for a moment and let's see. Then there's this thing called, so at first he implements it with just the number 532. Then he does this dynamic loss scaling where he, and he says the annoying thing is that it introduces a new hyperparameter, which is the 512, right? That you multiply the multiplier of the loss function. So he introduces this new concept called dynamic loss scaling, and he implements it. And what you do is you scale the loss, and if the gradients don't blow up, then you scale it again by a factor of 2, and you keep scaling it until you make the gradients blow up, and then you back off by a factor of 2, and then that's the number that you use. And that way you get a better, you can make the gradients as large as possible. That's the idea, as large as possible without making them overflow. So that's what the dynamic loss scaling does. And it's just interesting, he had this function to test whether you got gradient overflow, and he calls it test overflow. So he builds this function, and all it does is it asks if the number is infinite or negatively infinite, or if the number doesn't equal itself, which means that it's a NaN. So it's testing for 3 cases where you don't get a number, where you got overflow. So he builds this function test overflow, and then he times it, and it takes 252 microseconds. And then he compares it with the native PyTorch function, which checks for NaNs, which basically is doing the same test, right? And it's in the first time I ran this, it was actually slower than his function. But then I thought, well, why do I need this item at the end? The item leaves leaves it in a tensor form, so it's either true or false, but it's a tensor, true or false. If you take off this item, then it's just much faster. I don't know why, but this function can no longer be said to be faster than the PyTorch implementation, as Jeremy said before. I don't know why I guess converting that item, converting this tensor, because when you just use this part of the function, you end up with a tensor output. And then by taking this, chaining it with .item, it converts it into a Boolean. But a tensor can also be true or false, and so it's just as good as a Boolean. You don't have to convert to Boolean. And if you don't do that, you get a much faster function. So anyway, that was just interesting. And so now, and here his final version of this mixed precision callback that implements the dynamic loss scaling, that's the last thing he does here. And let's see. I ran it 10 times just to see if it's better, but I didn't do the statistics, so I didn't really check the final step, because I was interested in if mixed precision with dynamic loss scaling is actually better than not mixed precision, but I didn't get around to checking that. Let's see. So let's go back. So let's go back now and spend some time to understand this diagram, because I think Christine is right. I'm a little confused by this thing too. Okay, so first I guess you just copy the model to half precision, right? And then you do a forward pass on that with the half precision data and model. Then you convert it back to full precision loss function. Then you scale it by multiplying it by some number like 512. And now you have this scaled loss, which gives you scaled gradients when you do the back propagation. And here it says you do the back propagation in FP16 in half precision, because I guess that's where because the whole idea here is you're looking for speed, and the gradient computation, the back propagation is one of the time bottlenecks, and so you do that in half precision to get more speed. And I guess the forward pass could also be a speed bottleneck. So you're taking advantage of these two speed bottlenecks to do things in half precision and get greater speed. Okay, now what happens after this? He copies the gradients to FP32 to keep track of the small part of the number. Then he divides out the scale factor so that it restores it back to what it should be, what the gradients should be if you didn't scale the loss function. And then you copy them to the master weights. But I think what he's doing here is he's applying, when he says apply, he means apply the update. So you're using the full precision gradients when you calculate the update step. And I think he gave the reason for that it's okay to have, let's see, he said something like it's okay to have the gradients and the weights in half precision, but that when you calculate the step, it should be in full precision. So a little bit confused by that. Maybe someone can weigh in with their understanding of this mixed precision training if you've looked at this carefully. So he has two. Well, let's first look at the first. He first talks about these 5 steps. Then let's see. Okay, then the next he applies the loss scaling. So the first step is without loss scaling. So it's just the simple version of the model. So let's just look at it. He says compute the output with the half precision model and then the loss function. So that's to get the speed there, right? Then you back propagate the gradients in half precision, again, to gain the speed. But then you copy the gradients to full precision and you do the update in full precision. Then you go back to the half precision model. So and then you just keep going in this cycle. And then the next one he does, the next description of this is that he adds in this this scaling. So okay, so now instead of step 2, which was just back propagate the gradients in half precision, you first scale the loss function and then you back propagate in half precision. And that's an advantage because now the gradients are going to be larger numbers, because if the gradients were really small numbers, they could round down to 0 when you go to half precision. And so that's the reason for loss scaling. You scale everything up by a factor of, the default was 512, and now the gradients are less likely to be dropped because they're less likely to be rounded to 0. That's what he's showing here, is that if a number is smaller than this, then it will be rounded to 0. That's what this drawing is showing. So he's basically shifting this whole histogram to the right by loss scaling, and that puts the gradients in the representable range. Okay, but you don't, you have to remember to unscale them later on. So so you first do the loss scaling, and then you get your gradients that are scaled up, blown up by a factor of 512. Then you for the update, you copy them to full precision, and then you divide by the scale factor, and that puts them back. That means your gradients are what they should have been in the first place if you didn't do the scaling. But now they're in full precision, and so they won't be set. Even if you divide them by the scale factor, they won't be set to 0 because they're in full precision. Does that make sense? Okay. If you didn't do this step, if you copied the gradients in half precision and then you divided them by the scale factor, then the scaling was for nothing because they're going to get rounded down to 0 again, right? So to keep that advantage of the loss scaling, of the scaling, you copy the gradients to full precision, then you divide out the scale. And now the gradients are what they should be, but in full precision, they won't be, the small ones won't be made to 0. Does that make sense? Okay, and then when you do the update, you do it in full precision, and then you copy over the model to the half precision, and then you do it for the next step. So does that make sense?
I think so. I think what I'm realizing is that when he went through the picture, he talked about doing back propagation at 16, and I think the way the picture looked, I thought it was supposed to be the copy part that was supposed to be at half. But it makes a bit more sense to me.
Yeah, I mean, to me, this the bulleted point, the numbered points, that makes sense. And when I look at this drawing, it doesn't seem consistent with. I don't understand. The drawing seems a little bit inconsistent with the bulleted steps there. But I think the main thing to take out of this is that we want to do the forward pass and the back propagation in half precision in order to gain speed and memory. But we want to do the gradient update. When you calculate the gradients and you update the model, you want to do that in full precision. And I think this whole process wouldn't make any sense without the scaling step, because otherwise you're gonna, your gradients are gonna underflow and you won't get good results. So when you scale the loss function, you get scaled gradients. Then you copy those scaled gradients, which are blown up by a factor of 512. You copy them to full precision. Then you unscale them. That is when you divide by the scale. But now they're in full precision, and so they're not going to underflow. Does that part make sense? And now when you have the gradients in full precision, that's when you do the update. And then you do the next, and then so you just keep doing this cycle from for each update step. So I think I understand it in terms of these 5 steps, but I'm not sure I understand every picture in this drawing, because he didn't say that the loss function is in F32. It's in full precision. Well, here he did. So you do the forward pass in half precision, and then I guess you compute the loss in full precision. Okay, he didn't say that up there. See, so in this, he must mean that you then compute the loss in full precision, because that's what he does here. Then you scale the loss, multiply it by 512. Then you do the back propagation, but the back propagation is supposed to be done in half precision. So I don't understand this step. You start with a full precision loss function. How do you do the back propagation in half precision? So that's a little confusing to me. That is, why is the loss function done in full precision? Okay, then anybody have any insight on that one? Going from a full precision loss function to half precision scaled gradients. I don't see how that's done. I mean, if you want the half precision gradients, I thought you would have to start with a half precision loss function. Because that's the whole idea of getting that speed. That speed is that if you compute all your derivatives and all the derivatives of the loss function in half precision, that's where you get the speed from the back propagation. So anyway, that's one piece I don't understand, is this piece here. I would have thought the scaled loss function should be in half precision. Okay, then next is you copy the scaled. Okay, this step I understand. You copy this the scaled half precision gradients to full precision, then you undo the scale, then you apply the update step. So this part is all clear. So to me, the only thing that's not clear is this part. Why are you using the loss function in full precision? And he doesn't say that. He doesn't say anything about the loss function being in full precision up here. So anyway, does anybody have any insight about that? That is basically this piece, the loss function being in full precision. That's the part that I'm a little confused about. Christine, do you have any thoughts about that?
No, I don't think I have any. I don't think I should say any more about it. I think what you said is correct. The bullet points were a bit more clear than the actual picture.
Yeah, but I mean, I think that if this is the only part of the actual picture that doesn't seem to be represented in the bullet points, is having the loss function in full precision. The rest of it, I think, pretty much follows the bullet points. Anyway, so that's as far as I want to get with this. I mean, it would be good to go through all this code. I've gone through about half of it to understand what he's doing, but it's very convoluted because you have to keep referring back to the data structures that he's defined from previous notebooks and so on. Anyway, the end result is you get this beautiful callback where it allows you to do the mixed precision. And then he adds the dynamic loss scaling and writes the callback again, but now it includes the dynamic loss scaling. And actually, I ran this, and it does tend to use larger scale. Let's see. I printed the scale, the scale after every run, like Jeremy did for the first run, and you find that instead of 512, it ends up using 65,000, which means, and what does that mean? That means that it can handle very, very small gradients without having to set them to 0, right? Because it's multiplying the gradients by 65,000 and then converting them to full precision. And then dividing by 65,000 again, and now in full precision, the gradients will be small, but they won't be 0. So that's what this dynamic loss scaling is getting you. Anyway, so that's the end of this notebook. Now let's spend some time looking at the inception. The ResNet notebook. I listened to his lecture a couple times, and I'm still not. I understand what the ResNet is, but not completely. So I think. I don't know. Does somebody else want to discuss this a little bit? I'm going to eventually go back to this drawing that he made. I think the thing to do that I didn't have time to do this week was to actually really review that bag of tricks paper, the section where he discusses the ResNet. But what I understood is, let me go to this PowerPoint because I think I have that from the paper. Let's see. I'll go back to the other one. Foundations. This one. Can everybody see this this ResNet drawing?
Nope.
No. Okay, that means my sharing has to be. Oh, that's right, because I was sharing the
notebook, right? Okay.
Notebook. Now I got to go back to sharing. So stop share, start share, and go here. Now you can see it, right? The ResNet.
Yes, I can see it.
Okay, great. And can I blow this up? So he in the lecture he talks about this ResNet D. I think I didn't get the whole picture. He talks about this ResNet D, and what it does is it puts together a few convolution layers like we normally do, but then it adds together something that, and initially Jeremy said that ignore this stuff. Just it adds together. It just passes through the previous layer. So you end up with this plus the identity, and so that's one form of the ResNet. Then he says that this average pooling layer allows you to do things like increase, like double the number of channels and let's see. He says that in normal operations, the grid that you start with, you have to maintain the grid to be the same size. In other words, the output of each layer has to be the same size so that they can combine with the output of the whole series of operations has to be the same size as the original one so that you can then combine them at the end. But then he makes some variations where you can change the size of, in one of these, you can change the size of the grid, that is by changing the number of channels and changing the number of outputs. And then he introduces this so that you can try to match whatever grid size you end up with this series of convolutions. You can do things like here, he's reducing the size by 2 with this average pooling. And that's so that he can match the size of the left-hand side. So if the convolutions are leaving the data the same size as the input data, then you just pass it through with no operation here and then you can add them together. But if you're changing the size of the output, then you have to match that with doing something to the input here on the right-hand side. And so that's why there's this average pooling step. So I don't have the whole drawing here. The whole idea of this ResNet thing is to be able to train very deep networks with lots and lots of layers and not have the gradients either underflow or overflow. And that's as far as I got with this ResNet so far. So does anyone have anything to add? Yeah, I'm sorry about this. I meant to prepare this, but I got so hung up on looking at notebooks B and C that the first two notebooks that I didn't have enough time to properly review the ResNet. So we'll just take that up next time. But unless anyone has anything to add.
We still have half an hour, right, Joseph?
Pardon?
We still have half an hour?
Yes, we still have half an hour. So we can start, if we want, we can start looking through the
I can take a stab at it.
Yeah.
And then maybe you can.
Let me go back to the code of the ResNet.
Actually it'd be nice if you can share this image and that code so that we can go side by side, if that is possible.
Well, I'm not sure I can do that. I don't know how to do that because that means you'd have to get them both into the same window.
Can you minimize this and pull it somewhere there, or just take a screenshot and have it somewhere then?
Or can't you share your desktop rather than sharing a window?
Oh, if I could do that, that'd be great. I don't know how to do that. Let's see. Let's see if I can stop sharing, and then let's see, share and show all windows. There we go. We can do that. Let's see. No, that's. Let's see what happens if I do that. What are you actually seeing now? I chose the option to share all windows.
Still see
I
the
think
pop-up.
now we can see your desktop.
Okay, you can see that. So if I move that out of the way, you can see stuff that's underneath it.
Yeah.
Oh, great. Okay, so that's good. So now I have this in the back. I have this in the background that we can refer back to when we need to. But what we really want to do is look at the code. And let's see. Yeah, here we go. So the first thing he does is he builds some of these functions that are going to help us. One is the no-op function, where he just passes through the original data, right? Then he builds a class, a flattened class, which basically just converts an image to a vector, the two-dimensional image part to a vector for each channel. So the output size is going to be, the number of items in your batch and the number of channels. So if you have 3 channels, there's going to be 3, and then each output is going to be a vector that has the length of, I think it's 128 by 128. So you basically converted the 128 by 128 image into a 128 squared vector. That's what this is doing. This flattened class. And then this one, it's just a convenient way to specify a 2-dimensional convolution layer. But I don't see why he went to all the trouble to make this, to define this thing, because the only thing he's doing is saving, specifying the padding, right? I mean, you could just, instead of using this conv function whenever you want to build a convolution layer, you could just go back to the original conv2d, and you still have to specify ni, nf, kernel size, bias, and stride. And the only additional thing you have to specify is the padding. So I don't see why he went to the trouble to define this, but that's fine. We'll just work with it.
3 of them are default parameters there, Jeremy. Oh, no, Joseph. So if you call con, you just need to specify ni and nf.
I see, because he put them, he
Right.
forced them to be. I see, that makes sense. All right, that makes sense. He forced them to be the defaults. So that's fine. So conv is just a convenient way to build this convolutional layer where everything else is specified except for ni and nf. Thank you for that. All right, then this is the activation function, which is defined as a ReLU. And so when you apply the activation function to the output of a layer, you just multiply it by a ReLU and you do it in place. So that part is easy to understand. Then he has this initialization function, and if the bias is not none, then you initialize the bias to 0, I guess. And if this is a 2-dimensional convolution, if this is a convolution layer, then you use Kaiming normal initialization, which we studied before. And then it's recursive, so that you go through all the layers, all the child layers, and apply the same initialization to them. So this part is fine, the initialization. So then he defines this function where you make a layer consisting of the convolution, a batch norm, and optionally an activation function. Because sometimes he builds a layer that includes an activation function at the end, and then part of the ResNet you don't want to do that. There are some parts of the ResNet for which you want to apply the activation function later. So that's why he has this option to apply the activation function at the end or not. And this is just what you'd expect. You give the input and output sizes. You specify the kernel size for the convolution, the stride, and then he's got this 0bn parameter that tells you if it's false, then if it's true, then you just initialize the batch norm, the weights to 0, and otherwise you initialize them to 1. So let's see, nn dot batch norm equals. Okay, so this is a batch norm layer. That's bn. nn dot init dot constant bn weight. So you initialize the batch norm weights to 0. Otherwise, if this 0bn flag is on. Otherwise, you initialize the weights to 1. Then you specify the layers that you want, a convolution layer and a batch norm layer, and optionally an activation layer. And then you build your convolution network with those layers as input. So this part is fine. The only thing I don't understand is this idea that this batch norm, this zeroing the batch norm, like you zero the weights or you make them all 1. And I thought we went to a lot of trouble to show that initialization is really important, and but now we're just initializing them to all zeros or all 1s. So not really sure about why they're doing that, but that's apparently a key step in the ResNet.
Jump back to the ResNet D diagram, Joseph.
Yes, let's jump back to that.
I mean, the way, so conv layer, finally, at the end of the day, you stack up the conv2D, the batch norm, optionally the ReLU, and the batch norm can be either initialized to 0 or 1s.
Yes.
And so the key idea here, like you mentioned in ResNet D, is starting from input to output, there's a con 1 by 1, con 3 by 3, and the last con 1 by 1 doesn't have the ReLU in it.
Correct, yes.
Point 1, right? So that ReLU comes after the output.
Yes.
Now, that last con has a batch norm, and that is the one, when we look at the res block, we'll see that that is where the batch norm is set to 0.
Is
and
it this one here? Is it this one here, the last?
Right, right.
The last, what about this one?
That one, hang on. I don't think that one, because that one basically is just to control the depth. It's a 1 by 1 comp, right? So that's basically trying to control, if you change the filters, number of filters on the left-hand side, you want to change the number of filters on the right-hand side.
Yes, that's what the average pooling does, right?
The average pool is more for the spatial dimensions. So that's height and width, right? You're striding by 2. Yeah. So that changes the spatial stuff, whereas the con 1 by 1 changes the depth stuff.
Okay.
So if you switch back to the left-hand side, the con 1 by 1 has a batch norm set to 0. So basically you multiply everything through this con 1 by 1, con 3 by 3, come through the con 1 by 1, and then batch norm is 0. So you're basically multiplying everything into 0. So the left-hand side is 0. Right-hand side, you're not looking at this current block, you're actually looking at the identity. So you're passing the input straight through. So at the end of the day, your output is input plus 0, which basically is just the input. So what Jeremy says is that this is a great way to initialize stuff. So that's why this is being done. So that is the part of the ResNet D that we kind of covered right now.
Yes, but so I got that part in Jeremy's discussion. So what you're saying exactly is exactly what Jeremy said in the lecture, and I heard him say that, but I don't understand why. Why do that? I mean, what have you done when you've passed through the initial data and done nothing to it? So what's the point?
You're just setting the initial weights, right? That's all you're trying to do.
Yeah, but you don't. I mean,
the training happens after this, right? I mean, what is your other option? Your other option is to kind of use chiming to initialize stuff, right?
Yeah, which I thought we had. We saw that in his definition of that conv function. He used chiming initialization. So now I'm confused about why we would go back to initializing with zeros or initializing with ones.
Going back, okay, that's a good question.
That bn command, that bn switch that he had in the, where is it?
The conv layer 0 bn.
There's a bn. Let's see, I saw it. Let me just go back to the full thing for a second.
From the conv layer 0 bn, the switch, right?
Yeah, conv layer 0 bn. That's the switch. 0 bn. So if 0 bn is false, he initializes the batch norm to zeros, and otherwise he initializes sorry, the weights in the batch norm layer to zeros. And if it's not false, then he initializes them to ones. So this is the part that I don't really understand why, or this is one part that I don't understand why. And he says it's, and like you said, he said it's a great way to initialize, but I don't understand that.
Yeah. Yeah, maybe next time.
Yeah, but the interesting thing is you can see the res block architecture here, where because you know, you look at that drawing that we saw, and you ask yourself what's going on there. He's basically forming two different networks, and then two different convolutional networks, and then he's adding them together, and you see that right here. So in this class res block, is everybody seeing what I'm seeing? I'm looking at the res block class.
Yeah.
Yes, I can see it.
Okay. So at the end of the res block class, he defines this forward method, which returns. So he's building two blocks, and then he's adding them together. So let's look at these. Maybe we should spend a little time looking at these two blocks and understanding what he's doing here. So he initializes the input and the hidden layers. And then there's this expansion, which you can, I guess it's a Boolean or something. Oh, no, it's not. It's just a number. So expansion is something about how to make the ResNet bigger. So because if expansion is, so expansion can be either 1 or some other integer bigger than 1, I think.
I think it's 1 or 4.
1 or 4. Okay.
So it depends on whether you're using a ResNet 18 or a ResNet 34. For the smaller networks, you don't want this bottleneck layer.
So that's 1. So for ResNet 18 and 34, expansion would be equal to 1, right?
Yes.
And then for the larger ResNets, the 51 and the 101, then
4.
Expansion is 4. Thank you. So, and what does that do? Well, it just replaces the number of layers with a factor of 4 times more.
Right. So basically, you're going down. If you again go back to the diagram, or if you think about the diagram, you start with a 1 by 1 conv, go into a 3 by 3 conv, and then a 1 by 1 conv.
Yeah.
So larger networks in the 3 by 3 conv is where you want to kind of reduce the number of layers because of computation, I would assume. So that's where you go. That's where the bottleneck is happening. So you divide by 4 for the 3 by 3 conv, and then you jump back up in the last 1 by 1 conv.
Where do you divide by 4?
If you actually, this is just part of the ResNet block. So if you move down to the XResNet,
Ah, okay.
do you mind pressing escape and L? So I can just tell you, yeah, escape and L.
Escape L.
Even on the bottom cell.
That didn't.
Yeah, it did. It did work on the up one. So even for XResNet, if you do that.
What does escape L do?
Just add line numbers, so I can just tell you line numbers.
Oh, okay, there we go. That's great. I didn't know that. That's a great thing to know. Okay, so here's line numbers for XResNet.
Yeah, so in XResNet, if you look at line number 9, you're doing 64 by expansions.
Ah, okay. And expansion is either 1 or 4.
Yes.
Okay, so it compresses the
right.
The network. Sorry, it compresses it.
Number of channels.
Specifies a smaller size layer.
The number of channels become less.
Number of channels, yeah, in the layer. Okay.
And then going back to ResNet block, if you actually look at line number 17, like you were pointing out, you're basically doing activation function. That's basically the ReLU. That's what, if you look at ResNet D, you saw was applied after the plus.
Yeah, that's on the, but let's see.
So the left-hand side one, and there's a right-hand side part to that equation, right? So the plus. So the stuff before the plus is what is happening in the left-hand side of the ResNet D. So if you again pull back that diagram, we can compare with that. That's the easiest way to kind of understand.
Yeah, but I thought the activation function is supposed to be applied after they get added together.
Yeah, so that's why it's
Oh, it is.
outside, right?
That's right. Yes, exactly. So here's the parentheses. So what you're doing is you're adding these two things together,
Mm-hmm.
and then you're applying the activation function on the result, which is exactly what he said. Good.
Right.
Okay, so now we should just look at what these two things are for a minute, so that we'll understand what's being added together. And presumably one of them is the left-hand side
Right.
of the resonant diagram, and this is the right-hand side.
So the ID conv is basically identity convolution and the pooling layer. So that's what you already saw, right? You had the average.
The ID conv is no op if the initial and final layers are the same. Otherwise, so it's making them match, I guess, right?
Yes, exactly. So ID conv takes care if number of filters are not the same.
Yeah.
And self.pool basically takes care if the strides are not the same.
Yes. Okay.
Rather, if stride is not equal to 1, because if stride is equal to, that means you've changed the size. So you have to do that on the right-hand side too.
Yes, great. So that's what. So this part is just making the right-hand side match whatever architecture you've chosen for the left-hand side, so that you can add them together and they have the same number of things to add together. The tensors will be the same size. So back to the first one. So now we understand the self.id conv and we understand what this is doing here. Now let's see what self.convs is doing. It's basically, we're specifying layers depending on what network we're building, I guess. So here's where we specify the layers. If expansion equals 1, we're going to do it this way with this conv layer followed by this conv layer. Remember, the final conv layer doesn't get an activation function, so it's only 2 conv layers. And I guess that's for the ResNet 18 and 34.
Right.
And then if expansion is 1, if expansion is not equal to 1, then you do this else block, which means, and I guess Jeremy's code is if expansion is equal to 4, is bigger than 1, then we're doing the larger ResNet, the 51 or the 10, whatever it was, 50. What was it? 51 or 101? The larger 2 ResNet. And so in this case, we're building 3 layers. The first layer, the second layer is the same as the first layer here, and the third layer is the same as the second layer here, except that the kernel size is 1 instead of 3. And again, the final layer has to have no activation function because the left-hand side of the ResNet, remember the activation function, you add the left-hand side and the right-hand side, and then you apply the activation function then. So on the left-hand side, the last layer doesn't get an activation function. Either way, whether you're building the larger or smaller networks. And 0BN is true, which means that all the weights are going to be set to 1, I guess.
No,
so
0. Right?
The batch norm weights are going to be set to 1.
0.
Okay. Oh, I thought if it
1.
was true, they got set to somewhere in here.
Yeah, again, where you're highlighted right now.
There, 0BN.
If 0BN 0.
True, that's right. If it's true, they get set to 0. If it's false, they get set to 1. Got it. Okay, right. So this is setting all the batch norm weights to 0. I'm still not understanding why that's being done, but it's apparently very important for the ResNet. Okay, so you specify your layers, then you build, these are the layers for the left-hand side of the ResNet. Then you build that network with those layers. And then the next 2 lines are building the right-hand side, which is to match, which is basically an identity passing through the original data or activations with no change, but you have to do this little tweak to make them match because whatever you did on the left-hand side to change the size of the output, you have to do the same thing on the right-hand side, and that's what these last 2. That's what these 2 functions do. They make the right-hand side match the left-hand side. We just went over that. Then once you've built those 2 sides, the left-hand side and the right-hand side, you then add them together and apply the activation function, which is a ReLU. So that's clear enough, I guess, what the res block does. And then ResNet apparently will put together a bunch of these res blocks. Let's see.
XResNet starts off from a copy of ResNet C. So if you look at the ResNet C diagram.
Okay, let's go back and look at that. And unfortunately, I don't have the labels of which one is which. This is D, right?
Right, the middle one.
The middle one is D, and this one is C, right?
Oh, no. I just look at the, yes, that is A. I mean, that is B.
Oh, okay, this is B, and then this
No,
is C?
no, sorry. The one
Right.
where you're currently at is B.
Okay.
The one beside that is C. That's the middle, yeah. And the one after that is D that we just.
Okay, right. So C is different because it doesn't have the two sides.
So C's main point was basically they started off with a 7x7 conv. And the whole thing was that why do a huge 7x7? It's first of all more expensive to compute, and it's equivalent to a single linear function, right? Mm-hmm. So break that 7x7 to 3 consecutive 3x3s. You're basically essentially covering the same receptive area of a 7x7. So that is the tweak here. Instead of doing one huge 7x7, you do 3 consecutive 3x3s. Follow that up with a max pool.
Okay.
So doing 3 consecutive 3x3s is in itself like a mini neural network. So it's extracting more features and doing a bunch more of stuff than what a 7x7 would do. So now if you look at the code, that should start off from there. That's what the stem of the XResNet is.
Okay, great. Thank you. So now let's go look at that code where XResNet starts off. And now we have the line numbering, thanks to Srinivas. So now, Prashant. So now we have 2 things.
Right, starting off from line number 5, he defines the number of filters that he wants, and he's doing some things which can be dynamic. So CN is usually 3 because you're dealing with colored images.
Yes.
The second one, if it were 3, then it would be like 4 into 832, which is a suggestion which was made in the XResNet paper. I'm sorry, in the Bags of Trick paper. And the other thing what Jeremy was mentioning there is that no one apparently has done it in such a way where you can dynamically tweak. So now if you go back to a grayscale image, you would end up only with 8 there. Or if you end up with, I don't know, MRI images or spectral images, where if you have 4 channels, then you're automatically changing that to like 4 + 1, 5 into 8, 40 channels there. So that was some tweak that he thinks is, pretty cool in terms of how dynamic that is.
Yeah, and he also mentioned that somehow the NVIDIA chips like multiples of 8.
Oh, right, correct, yes.
So that was the reason for this multiple of 8. Everything has to be a multiple of 8. So then he builds this stem layer. Okay, so it's
so if you again look back at that diagram, actually, if you just look at the code, line 7 is basically going for I in range 3. So that means you're running the loop thrice.
Right, he's building 3. He's building, the stem is going to have 3, is going to be a list of 3 conv layers, right?
Right. Where remember that each conv layer, again, is basically a convolution batch norm ReLU. Yeah. And the only thing, again, if you go back to the diagram, you can see is that only for the first conv do you want a stride equal to 2.
Yep. So
that's all he's written that in code there. So that's pretty much the first part of the SEM without the max pool.
Okay, so here we can see the drawing and the code side by side. And this is the one we're looking at. And the first layer is stride equals 2. Yep, and then the next layer is just 3x3 with a stride equals 1. And so that's what.
Again, some reasoning behind why you want stride 2 at the first one there after performing the 3x3 is kind of you're reducing the size pretty much immediately. So you're computing on less data, so it should be faster. Mm-hmm. Yeah, the arguments which are made both ways, like for the 7x7, or rather when we move further ahead, you'll see the other tweak in ResNet be why they moved the 2x2 convolution from the very first con 1x1. So actually, when we get there, you just keep this point in mind, so it'll make more sense then.
Okay. So there, we're building this series, this set of 3 layers. then we are specifying the number of filters in each, let's see.
Right, so that basically number of filters again is kind of dependent. The first one is kind of dependent on expansion.
Yeah.
So there, yeah, if you have expansion is equal to 1, which is usually set for the smaller ResNets, which is ResNet 18 and ResNet 34, you basically end up with 64, 64, 128, 256, 5, and 2. Anything bigger, 50 and bigger is where they kind of set it to 4. And that's where the bottleneck comes into picture. So bottleneck, all it's trying to do is, the example he also gives is like, let's say you start with 64 filters. When you jump into this one, it'll be 64 by 4, so that's 16 filters. And then when you come back out, it's again 64. So that's where the bottleneck is happening. You're squeezing 64 channels down to 16 channels and then squeezing it back up to 64 channels.
Okay. And is there a reason for that? Does it save you time?
I remember computation was one part of it. I can't remember. There was something else. Like bottleneck layer is, yeah, something not exclusive to the ResNet. I can't remember what else it was.
So it must save you time since you're building a larger network, and so this might.
Right, that is one reason for sure. Yeah.
Okay, so then he says he specifies res layers, make layer. I don't see.
Make layer is right at the bottom there at line
There
number.
we go.
Yeah.
There we go. This is a function, a helper function. Let me expand this a bit. Okay, is it all in the same screen now for everybody?
Yep.
Okay, great. So there's the make layer function, and it takes in an input and an output size, the number of blocks that you want to make, and its stride, and also the expansion number, and it returns a block, a network that's consisting of all the. It builds a series of res blocks, which now, sorry, I'm going to go up for a second. Res block is the upper one. Is the one we went through already? It's this one. Right. So we're building a bunch of res blocks, and it knows to.
So again, I think if you look at cell number 9, it's kind of helpful to see how you create one of them. So it says xresnet.create, the one below that.
Yeah.
No, sorry, the cell below that where you have 9.
Oh, yeah.
Yeah.
Okay.
So if you just look at xresnet.create, the first number in that is basically the expansion.
Yes.
And the numbers to follow that is basically your blocks, how many of them you want. And that's what you be.
The one thing, I mean, it's a detail, but I found interesting is by the time you get done with this, though, with the suggestions, the names actually don't precisely match. The ResNet 18 is actually more than 18 layers.
Right, true. Yeah.
It's 4 times, it's 8 times 2, 16, and then there's 3, whereas our name still sticks with 18. And it's the same as you go down. 152 is much more than that.
Larger, yeah.
So let's see.
One question I had on this was, when he does for the ID convert, which is keep the convolution ratio the same where no op, he does that based on if ni equals nf.
Right.
NF. And that just seems. I was trying to kind of grasp the intuitive way of thinking about it rather than just it's the fact that if the input equals to the output layers, and is that an artifact of the way he has it set up, or is that?
You can't add them otherwise, right? The right-hand side and the left-hand side cannot be added if either the number of channels are different or your spatial resolution, which is height and width, are not the same.
So he just goes off of that basis.
Yeah.
So he's checking the number of input channels to the number of output channels, but maybe he should actually check everything else too, the whole, to make sure that the networks have the same size tensor.
That is the next one, right? So stride is not equal to 1 will take care of that part.
Yes, but this isn't sufficient to prove that the tensors are the same size, right? It works because, well, it works in this special case, but I think in general, you might want to test that the tensors are actually exactly the same size.
I guess.
I'm not sure. I'll have to think about that. But anyway,
Question,
yeah,
I think the other part is he's trying to code if they're not equal, what would you do, right? So the first thing is if the number of channels are not equal, you fix it by doing the conv layer NI, NF.
Yes.
Using a 1 by 1.
Yes.
Whereas if the stride is equal to 1, it is no op, which means you haven't really changed the dimensions. I agree. I mean, I guess this is specific for XResNet.
Yeah, it's specific for this.
Yeah, that's kind of what I was saying, that it's somewhat specific to the XResNet way of coding stuff, I guess.
Yes.
But I guess that part of the code should work for any ResNet block, though, right?
Yeah, any ResNet
Structure.
block, provided
Right.
the two go together.
Yeah, exactly. If you have to do that combination step at the end, then this logic kind of should work there.
Should work, yeah.
Yeah. So this is really neat. It's kind of an automatic way to match, the right-hand side to the left-hand side. It's kind of very nice. And okay, so let's make sure we understand. So this has been really helpful. Now I understand what's going on here, and I'm close to understanding what's going on in the rest of it. I still don't understand why why this 0BN.
Yeah, I'll think about next time.
Why you have to pay attention to that and change the initialization of the weights. But I'm going to read the paper for next week for sure. So.
That one is mainly, at least my understanding, having gone through the papers, is on the output of the ResNet block, you just want to make sure that when you initialize, you set it up for identity so that the network learns quicker. That's all it is. So the 0BN equals true just says make the batch norm, and then we scale, and the scaling of the non-bias make that 0 so that you don't scale, and which means basically you're just identity. You don't do anything. You just normalize and you pass the X through.
Right. Yeah.
And that's all you're doing. And so you do that on the last stage of your ResNet block so that you get the identity going through, and that too at initialization. So it initializes faster. And that's just empirically determined that it initializes faster. Or the network works better when that's the initialization.
Okay, so this block here comes before this res block C in the ResNet. Is that right? Or how does that work? Let's see.
Typically, it's the last block going out.
Oh, res block D is the last block going out.
Actually, in theory, right, Srinivas, on the left-hand side, if you set all those last layers to 0, it still, in essence, is the same, right? Because I
have to look in detail whether it does that on the left or the right, but the net effect is to 0 so that it gets the identity.
It should be the left because the right is just the identity pass, right? You're just getting the input back.
So it is the left.
So this is where the batch norm is initialized to 0.
Right.
Okay.
But that's what I'm saying. I don't know, at least from what I'm thinking, in all those convs on the left-hand side, if you set BN 0BN is equal to true, that should still work, right? Because you're basically trying to zero out the left-hand side and just try to pass the input back to the output.
Yeah, but it may not be necessary.
Yeah, exactly. That, yes.
He only does it on the last column.
Yeah.
On this one here. The other ones have.
So others may scale and it may still have the no impact.
Anyway, so there we are. We've gone through pretty much all this. We haven't quite finalized our understanding of this, but we can do that next time. And then he uses this function, this xresnet function, which he's really proud of because it fits on one page, which is really pretty cool. It fits on one slide. You can see the whole thing. And then he uses that to build this one function that he built, this one class. He uses it now to build ResNet 18, ResNet 34, ResNet 50, 101, and 152, all the commonly used ResNets. And then
yeah, and at least, I think a good way to check your understanding is to figure out how many layers from just the xresnet formula and see whether, that itself helps tell you whether you can grasp what's going on the rest of the code behind it.
Yes, that's a good point. So
yeah,
go ahead. Go ahead.
For example, the very first xresnet 18 or xresnet 18 is 2222, which means there are 8 of the rest blocks, each of them of 2 layers because it's less than 50, so it only chooses the 2.
Right.
And so that is 8 times 2 is 16, and then the stem, which is 3 layers actually, and so it's 21, and then anything else you do outside, such as the there's some pooling and stuff that he does in the code, which so eventually you end up in the 20s, but the 18 is because in the original there was just a 7x7 outside of these rest blocks, so that's why it's an 18.
I see.
Because it's 2 times that, and then when you come to 50, it's 3 times the sum total of these layers. So what you're passing in here is the layers, and so it's 16, the sum total for 50. 16 times 3 is 48, plus the 2 in the stem, which is the 7x7 and whatever the pooling should have given you 50, 48 plus 2. But now we do more, we split the 2 in the stem to 3, and then he does an average pooling and then a full a flattened layer. So it kind of is a little more than 50, but that way of calculating gives you the understanding of what is behind each of these calculations or each of these layers, and then you can make sure that the code above ends up providing you what you need.
Yes, that's a good way to check when we've understood the code to try to take this apart and understand each piece of it.
Yeah.
So
has anyone figured how to print out graphs? Like on TensorFlow, you can print out like a model graph and it'll exactly show you what the sizes are and like a flowchart. I have not figured out one in PyTorch. Does anyone have any suggestions if they've tried out? Because that really helps. You're looking at a diagram and you can follow exactly layer by layer.
Maybe someone has written a callback to do that and you can check on the forum to see if, chances are somebody has done that,
Okay.
Maybe, I don't know. Anyway, so the rest of it is just, he determines a good learning rate by running this learn.recorder. He plots the learning rate versus loss. I put labels on this plot because otherwise it reminds me what the plot is. Otherwise I forget what's being shown. And it would have been easy to put that in the original callback to actually put labels on the plot. But anyway, so I just added them afterwards. Let's see. Then he adds some scheduling, and he builds this little tiny function called create phases, and all it does is if you give it an input of 0.3, it will give you the rest of it, and it will give you a list of 0.3 and 0.7 because they add up to 1. If you give it a list of 0.3 and 0.2, it will correctly figure out that the last entry should be 0.5, and it'll give you that back. But if you give it a phase of, it doesn't know that these phases have to be positive and that they have to, all it knows is they have to add up to 1. So if you give it a phase of -1, it will come back and give you the second phase of 1.1, so they all add up to 1. And the same thing is if you give it this list of 0.7 and 0.8, which add up to 1.5, it will say, oh, the third phase you need is minus 0.5, and that makes them all add up to 1. So it's just a nice little function that helps you to create a learning schedule, right? And so he creates 2 schedules, and one of them is for momentum, but he's using this cosine 1 cycle thing that he created before, which is, it's a cosine annealing function. Then he puts together these 2 schedules, and then he runs he runs it with these schedules in place and gets a nice result. And then he just refines this a little bit, this CNN learner to it's doing the same exact thing, and it gets the same result too at the end, pretty much the same. But this is just for convenience. He puts all these things together in a more flexible format so that you can set all these switches. You can change the switches if you want a progress bar, or if you don't want to, if you want it on the GPU or not, if you want mix up or not, and so on. It builds the ResNet for you. And then he basically says, he gives you a link to his real training script that they used to get their Dawn Bench mark that they got last year. Remember they won this competition for building a very accurate and quick network that processed the ImageNet database. And he actually gives you the script that they used. The only thing different that we haven't seen here is that he modifies the script to handle multiple GPUs. So there it is. Okay, so next time we'll come back and just finalize our understanding of the ResNet, and then we'll also move on to the next topic, which is, I think, the transfer learning. Okay. Any comments or questions? All right. Well, thanks everyone. We'll see you next week, and continuing on in 12. I think we'll finish lesson 12 by the end of November, I think, or either that or maybe either. It just depends on how things go, because things are really getting to be dense. Like I was listening to Jeremy's ResNet discussion, and I kept having to pause and rewind because in 20 minutes he says so much stuff that it's really that 20 minutes is really a whole hour's worth of lecture. So and I don't know how dense things are from here on out, but given that in the rest of this is only the first part of lesson 12. In the rest of lesson 12, they're covering the entire subject of it. We'll see how that goes here. Okay, well, have a good rest of the weekend, everyone, and see you next week.
See you next week. Thanks for listening, Joseph.
Thank you.